Welcome to the lecture on grain structure during solidification in welding. So, we will talk about after the solidification starts in welding, then what way the grain growth takes place, and we have already discussed about this phenomenon which primarily takes place in welding, that is epitaxial solidification or epitaxial growth. So, we will have the idea about the epitaxial growth as well as the non-epitaxial growth, and also how that nucleation starts. So, about these things we will have the discussion in this lecture. So, in fusion welding, the existing base metal grains at the fusion line act as a substrate for nucleation, and being in intimate contact and wetting completely, crystals nucleate from the liquid metal upon the substrate grains without difficulties. So, as we have seen in the case of nucleation, so we understood that nucleation is normally of two types. So, you have the homogeneous nucleation and you have heterogeneous nucleation. So, as we have seen that in the case of heterogeneous nucleation, again the particle to nucleate from the substrate, there are few things which are coming into picture. The one is the surface energy terms, another is the contact angle, and based on that we already had seen that you have the activation energy formula that was there. So, the energy barrier that has to be that has to be overcome. So, that basically can be computed with the help of the formula, and there it was 4 then gamma cube, and then you have a term of Tm square divided by 3 of delta H and delta T square. So, and then in the bracket term you had 2 minus 3 cos theta plus cos square theta. So, in that basically we had seen that depending upon the theta value, this barrier for the nucleation which has some value in relation to what is required in the case of homogeneous nucleation. So, that factor can be computed for different value of theta, and when your theta is 0, that is there is complete wetting. In that case the term inside, that is 2 minus 3 cos theta plus cos square theta. So, that term becomes 0. So, your energy barrier becomes 0. So, you do not have any difficulty in nucleation. So, that is how. Now, in those cases what will happen, that you will have a growth, and typically what you see in welding, that you have the, if you have the similar material which is present and which act as the nucleation sites, then the further and further the growth takes place. So, that is the case of the epitaxial type of solidification or epitaxial growth. So, that is how it is defined in such cases. So, we have already seen that when we saw that when we have a substrate, suppose you have a substrate here. So, and for the crystal which is here, so this is suppose crystal which is to nucleate. So, this is C, and this is your substrate. So, that is denoted by S, and this is liquid. So, this is L. So, we have already seen that if this theta is the contact angle, so you will have surface tension term gamma LC, this value, and then you will have gamma CS. So, this will be here, and similarly you will have the gamma LS, and we have already seen that so this will be the radius r in this case. Now, we have seen that if you talk about the energy barrier which is to be computed, so for the crystal to nucleate, so that is actually 4 pi gamma LC square and Tm square divided by 3 into delta HM delta T as whole square, and in bracket we had 2 minus 3 cos theta plus cos square theta. So, that is what was the equation expression for the energy barrier for the nucleation. Now, as we see, when there will be mostly in case of autogeneous welding, when there is no filler and when there will be complete wetting characteristics. So, in those cases when it becomes theta as equal to 0. So, this term will become 0. So, your delta G becomes 0. So, so when the metal in the weld pool is in intimate contact with the substrate grains, so then it will be the case where there will be no barrier to the nucleation, and there will be nucleation without much of the difficulties. So, what happens that now in these cases when your there is no difficulty for the grains to nucleate. So, what will happen that the nucleation is occurring now in these cases the nucleation will be occurring by the arrangement of atoms from the liquid metal upon the substrate grains without altering basically their crystallographic orientations, and that is what is such process is known as the epitaxial growth. So, this epitaxial growth is normally so we have given this referring to the example of the autogeneous type of welding process. So, in these cases the growth mechanism that will be known as the epitaxial growth, or the nucleation also which is occurring the pre-existing grains which are there and working as the nucleation sites. So, that will be basically the epitaxial nucleation. So, normally it will depend upon if you have a material, so you will have a preferred crystallographic direction in which the growth will occur, and it will be looking like you suppose this is your weld pool. So, suppose this is your welding direction, and if this is the weld pool. So, what will happen that you will have a fusion line will be there. So, this becomes your fusion line, and on that fusion line you may have the grains. So, you will have the grains here, and then these so you have different type of grains like that it was there. Now, these grains basically will be growing, and they will be growing in these directions. So, what has been seen that for FCC or body centered cubic structures, now in these cases you will have the growing of the grains in this fashion, it will be moving. So, these are the for FCC or BCC, the preferred directions of growth are basically 1 0 0. So, they are basically the way they are moving, it is basically 1 0 0 direction. So, we know that this is the preferred direction of growth in the case of FCC or even BCC crystal structure. So, the trunks of the columnar dendrites will be growing in that direction and going towards this weld pool and go up to the center line. So, without changing their directions, basically these grains grow. So, that is your epitaxial growth in the welding, and that is what is written that in autogeneous welding basically nucleation will occur by arranging atoms from the liquid metal upon the substrate grains without altering their existing crystallographic orientations, and that is known as the epitaxial growth, or such kind of nucleation will be known as the epitaxial type of nucleation. So, this can be understood by referring to these macrostructures, and here you can see this is for the electron beam welding of the alloy. So, this is for the C103 alloy, and it is seen that you have the how you see that this is this dotted line, this is your fusion line, and what you see that this is the epitaxial growth from the fusion line going into it. Now, similar is the case when we go for the aluminum copper. If you look at the aluminum copper alloy, now in these cases this is aluminum 4.5% copper alloy, and here also you see that they are growing in one particular direction. So, that is your preferred direction of growth in such cases. Now, this is about the epitaxial growth. However, there may be the non-epitaxial growth also when you use the fillers. In those cases you will have the chance of non-epitaxial growth at the fusion boundary. So, in these cases when you are doing the welding with a filler metal, or we are joining two different materials, then the weld metal composition will be certainly different from the base metal composition, because there are two different materials being welded, or similar material being welded, but you have a filler material which is of different composition, different material. So, in those cases the weld metal crystal structure can differ from the base metal crystal structure, and in these cases when this occurs, the epitaxial growth is no longer possible, and new grains will have to nucleate at the fusion boundary. So, in those cases you do not have the complete wetting characteristics being satisfied. So, you will have the nucleation of the new grains, and so new grains will be nucleated at the fusion boundaries. So, and from there you will have the further growth of the grains. So, the fusion boundary will be exhibiting, so it exhibits random misorientation between base metal grains and weld metal grains. So, because they are not of the same material, so you will have the there will be certainly some misorientation between these grains, and so in these cases you will have the chances of heterogeneous nucleation occurring, and by that process basically the growth will be taking place. So, normally when we talk about the grain structure near the fusion line, in those cases, so away from the fusion line, the grain structure will be dominated by the different mechanism that will be known as the competitive growth, because what we see that you will have two directions of growth. One is your crystallographic direction and another, so that is your EG growth direction, and you have two way, that one is crystallographic direction, another is the growth direction in which the growth will be maximum, because that will be depending upon the direction of heat flow. So, so grains will tend to grow in the direction perpendicular to the pool boundary. So, however, columnar dendrites or cells with within each grain tend to grow in the EG growth direction. So, normally you have certainly, because you have one is your perpendicular to the pool boundary, another is in the EG growth direction. So, the grains with their EG growth direction essentially perpendicular to the pool boundary will grow more or more easily than less favorably oriented grains. So, basically you have two conditions of growth, and in that case wherever the grains which have their EG growth direction which is perpendicular to the pool boundary, that will so if these two conditions are met, in that case the growth will be more easily then basically where it is not meeting this condition. And when it is so only along that those grains which have these conditions satisfied, they will be growing, and this mechanism is basically known as the competitive growth. So, this is known as the mechanism of competitive growth in such direction, in such cases. So, basically we need to know the EG growth directions, and if you talk about the EG growth directions. So, you have for different type of crystals, you have different EG growth directions. So, if you talk about the crystal structure, and if you look at the EG growth direction, so that basically you must have the idea when you study these material science and engineering. So, if you talk about the face centered cubic structure FCC, now for them the EG growth direction is 100. Similarly, for the BCC crystals having BCC structure, again you have the EG growth direction as 100. Then for FCC you can we know that you have typical examples will be like you have aluminum alloys, or you have austenitic stainless steel. So, similarly for BCC you have carbon steels, and you have ferritic stainless steel. So, these are the BCC having BCC crystal structure. Similarly, you may have the hexagonal close packed structure, and it has the direction of 101'0, and then we know that for such materials like titanium or magnesium, they come under these type of crystal structure, and they have the value 101'0. This is their EG growth direction. And similarly, you have the body centered tetragonal. So, now in these cases you have the direction as 110, and the example is 10. So, this way your EG growth directions are there for for the different type of materials with different crystal structure. And the concept of the perpendicular phase, because that will basically give you the area of maximum temperature gradient or maximum heat transfer. And then when it is matching with when, so all those grains which are having the EG growth direction, and then they are perpendicular. So your grains with their EG growth direction essentially perpendicular to the pool boundary, they will grow more easily. So, others growth will be pinched off because they will try to grow in their EG growth direction, but then that is not basically having any perpendicular direction to the primary heat flow direction. So, they will be pinched off, and you will have the pinching off of certain grains, and then growing primarily columnarily of some grains which have that orientation. So, if you try to look at the competitive grain growth direction, so how you can see that if suppose you have this is the suppose weld pool, and this is being the welding direction. So, what will happen now? Assume that this is your fusion line. So, in those cases, now what will happen that you have the different grains which are there. So, now they will be shown like you have such grains is there. Now, what may happen that if so this will grow in this fashion, or that may grow. So, and this will grow in this fashion. So, this is your 100. So, and from here it will grow like this. So, this being 100. So, perpendicular to this pool boundary, basically your growth will take place. So, your growth is going like this. Similarly, this will be moving like and then so, and some may be pinched off like this. So, there may be some going like that, but ultimately the growth becomes like this. So, this is the example of the competitive growth mechanism in the case of welding. So, then we will talk about the effect of the welding parameters, and if we talk about the effect of the welding parameters like especially the welding speed. So, if you choose high speed and if you choose the low speed, in that cases the the orientation of the grains also they will be changing. So, you may have the low speed and you have the high speed. So, when your you have a low speed, then the weld pool shape is basically elliptic, and we have understood, we have already discussed about it, that when you are changing this speed, then at higher speed it becomes in the form of tear shape, and accordingly the grain orientations also, grain structure changes. So, when you have the low speed, now in those cases your the grains which you get, they will be having, this is the pool looks like, and that way your grains will be shown. So, in the middle it will be moving like this. So, this way your grains will be looking like. So, this is how grains will look in the case of low speed, and at high welding speed you will have the tear shaped pool. So, you will have so this way the pool shape will become, and in that case your grains will be straighter. So, that way. So, columnar grains are essentially straight when the speed is higher, and here it is curved to grow perpendicular to the boundary. So, that is the effect of welding parameters. So by looking at the structure, you can have the feel that how the speed variation will be changing the grain structure. Next thing which is important to be understood is the weld metal nucleation mechanism, and there is typically you have certainly, as we know, that there is region of solid liquid mixture in the case of welding. So, when we talk about alloy, so as we know that when we talk about alloy, so you have a region of mushy zone. Now, these mushy zones have the solid as well as the liquid region. Now, these regions, so now there are basically three possible mechanisms of the new grains to nucleate during the welding, and these three mechanisms are said to be the dendritic fragmentation, grain detachment, and the heterogeneous nucleation. So, what happens that when there will be convection will be dominating. So, what may happen that in the weld pool convection. So, if there is a weld pool convection, so that may lead to the fragmentation of the dendrites, and basically they will be towards the tip of the dendrites, and it is in the mushy zone. So, those dendrite fragments, they actually work as the nucleation points, and they will be acting as the new nuclei to form the grains. So, basically they are like the heterogeneous nucleation sites which occur in the case of welding, and this is frequently this is basically said to be a grain refining mechanism for the weld metal. Similarly, the second point is the, so one is your dendritic fragmentation. Then you have the grain detachment also is being experienced. So, what will happen that during if in the case of the weld pool convection, the partially melted grains, they will be detaching themselves from the solid liquid mixture, and then they will be again working as these as the nucleation points. So, that way they also work as the heterogeneous nucleation sites, and then many a times you have the heterogeneous nucleation. So, that is by the addition of, or by because of the presence of heterogeneous nucleating elements, or you may have many a times you have the foreign particles which are present in the weld pool, and these foreign particles which are present in the weld pool, they act as the nucleation sites. So, they also work as the place from where the nucleation starts. So, these are the three ways for the nucleation to occur in the case of weld pool. So, this is this has to be understood and so once we understood that you have the solidification taking place, solidification will be because of the thermal gradient, then we will be next we will be talking about what are the consequences of these thermal gradients, what are the distinct zones in those weldments. So, we will have more and more idea about the other aspects because of this temperature in the weldments. So, that is about this grain structure and their traits during the welding process. Thank you very much.